So I go to like a brief introduction about Sarath, who honored us with this interesting talk today. He's a former graduate of Mila, and right now a member of Mila CIFAR AI chair, and recently hired at École Polytechnique at the Department of Computer Engineering, and have lots of publication and a diverse interest, mostly focusing on machine learning, but and deep learning as well. And thank you very much, Sarath. Please go ahead.
Thank you. Thank you for the introduction, Wahid, and thank you for inviting me here. So, okay, so hello, everyone. But it's a bit weird to talk without seeing faces, but well, that's COVID. Okay, so I'll be talking about lifelong learning systems. What are they? So how can we design such lifelong learning systems, and what are the challenges that we have in designing such systems, and so on. But before I begin, I just want to give a very quick overview of my lab and so what kind of problems do we work on. Just a broad overview. So our lab is pretty diverse, as Wahid rightly pointed out. So we work in deep learning, reinforcement learning, and natural language processing. So we have a long-term research vision, which is to develop interactive learning algorithms that continuously learn from experiences. Okay, so now to achieve this vision, so we need to do a lot of work in different areas in machine learning, actually. For example, when I think about interactive learning algorithms, now this includes things like reinforcement learning, natural language processing for interaction through language, and sequential modeling, which is a major toolkit in both reinforcement learning and NLP. Similarly, when I talk about continuously learning from experiences, that's related to reinforcement learning and lifelong learning. So often the projects that we work in the lab are in the intersection of 1 to 4 of these 4 different topics. But for today's talk, I decided to focus just on one out of these 4 topics that we work on, which is lifelong learning. Okay, so now let's begin. So, well, I think we are in Montreal, so we don't need to sell the deep learning revolution here. Deep learning has made a lot of progress in the last decade or so, right? So starting with image classification systems, where with ImageNet, so we were able to achieve superhuman performance in the early 2000s, 2010s, and that led to a lot of progress in several other areas in machine learning. Just to give you some example, so DeepMind came up with AlphaGo, which is a Go playing agent, which could beat the human champion in the game of Go, which is considered to be one of the hallmark games for human intelligence, right? And similarly, OpenAI has been developing these enormously large language models with millions and then billions, now trillions of parameters. With such a huge model, so they are able to do a lot of cool applications, which were previously not even realizable. And DeepMind is also making a lot of fundamental progress in basic sciences. For example, they recently solved this 50-year-old open problem in protein structure prediction using deep learning, right? But there has been a lot of progress that has been made in the last 10 years. So if I have to summarize what we have achieved in a decade, I would put it this way. So given enough data and compute, we can actually solve simple mapping problems with superhuman performance. Okay. Now this statement is purposefully vague. So what do I mean by simple mapping problems? Some problems where we have a clear mapping from X to Y, and this mapping is also simple enough that it doesn't require a lot of cognitive load or a lot of reasoning capabilities, right? So that's what I call by simple mapping problems. So things like image classification or machine translation and so on. So if you have a simple mapping problem, if you give me lots and lots of data and probably thousands of GPU hours, then I can design a highly specific deep learning system which can achieve superhuman performance in this particular problem, right? Now the next question is this interesting? Well, obviously this is interesting for some people, who just care about that particular problem. But if you're looking for a system which is general enough like humans, then probably this is not the best that we could achieve, right? Like, so but there are a lot of limitations with this current generation deep learning systems. Like, for example, as I mentioned in the beginning, like, so they're extremely data and compute hungry. Like, you need millions of samples and you need thousands of GPU hours to train these systems. So this happens because there is not much knowledge transfer that is happening between the tasks, right? Like, so every time you want to design a neural network for a task, like, you start from scratch. Well, at max, we do pre-trained networks, but not more than that, right? Like, so there's not a lot of knowledge transfer that is happening between tasks in these neural networks. So this results in what I would call as narrow intelligence systems, because so these are highly sophisticated intelligence systems, like that can do a task extremely well, but just that task extremely well, right? Like, so I can develop a Go playing agent which can beat the human champion in the game of Go, but how easy it is going to be for me to repurpose this Go playing agent to have a conversation with a human, right? Like, so now that is almost impossible. So these are like narrow intelligence systems. And another very practical concern with current generation deep learning systems is like there is no learning after deployment. So you train a neural network, it achieves 95%, let's say, accuracy, and you deploy it in a product as a cloud service or in your edge device. Like, but once you deploy, then it becomes something like any other software engineering product, right? Like, so like it is just acting like an inference engine. There is no learning after deployment. Currently, if you try to learn after deployment, you will get into distributional shifts and like forgetting and like mode collapse, and like there are a lot of issues that will happen like if you're trying to learn online. Okay, so now these are the big issues in front of us. Now, I don't want to say that we have not made progress in any of these problems. In fact, we have separate fields focusing on all these four problems, right? Like, so transfer learning or online learning or multitask learning, each attempting to solve one of these problems, okay? But for today's talk, like, so I want to talk about lifelong learning, like, which is a learning paradigm which promises to solve all these four problems like together. So that's a big promise. So we need to first understand what is lifelong learning and like, so how can it solve all these four problems, right? Like, so now lifelong learning is not a new idea. So it exists for a long time, like since 90s, like from the earlier work of Sebastian Thrun and Mark Ring. The fundamental philosophy here is to design systems that can continuously learn over its lifetime. Okay, so now this paradigm also has a lot of names in the literature and hence a lot of confusion. Like, so some people call it as continual learning, some people call it as like never-ending learning. Like for me, they're all same, and for the purpose of this talk, we're just going to consider all these things as lifelong learning. Okay, now what are the advantages of learning continuously? So when you learn continuously, like you can be sample efficient. Why? Because you can transfer your knowledge backward and forward so that when you learn a new task, you can use all the existing knowledge that you have and learn this task faster, okay? Now, these systems are going to have some sort of general intelligence because they can pick up any task that you want them to pick up, right? And also, most importantly, lifelong learning systems can learn after deployment. This is just by the construction of these systems, right? Like, so they are meant to learn online and continuously, which means they should not differentiate between training time and deployment time, right? So now, this is why I said like lifelong learning is going to help us in solving all the four major challenges that I mentioned. Now, before we talk about the challenges in designing such a system in general, I want to give a quick one-slide overview of like different lifelong learning scenarios that one could encounter in practical situations. Like, so for example, first let's start with domain incremental learning, where the idea is, let's take image classification, for example. Okay, so I want to train an image classifier. I train with a particular data, I deploy it, and the quality of images shifts over time, right? Like, so maybe I trained it with like images from iPhone 5, and every year there's a new iPhone and the quality of images are just increasing, right? So this is a continuous shift of distributions. Like, so this is captured in the field of domain adaptation, but in this case, this is a continuous domain adaptation because like the domain shifts incrementally, right? Like, so now this is a lifelong learning scenario. So how do we deal with the domain shifts continuously? And the second common lifelong learning scenario that you could encounter is like what I call as task incremental learning. Here, the idea is you have a single system which learns to do image classification, then it learns to do image segmentation, then it learns to do image like super resolution and so on, right? Like so, or a visual question answering and so on. Like so, how can we design a single system which can pick up a bunch of tasks over its lifetime? And another really practical scenario that you could encounter is class incremental learning. So what is class incremental learning? Like, so again, let's go back to the image classification system. Like I have an image classifier trained with 10 classes, I deploy it. After a couple of weeks, the customer might come back and say, hey, I also want to classify a few more classes. So like maybe 5 more classes, right? Like, so now instead of retraining my system from scratch with these 15 classes, how can I just train with the remaining 5 classes and still maintain the performance from the previous classes, right? Like, so that is the idea of class incremental learning. Now, throughout this talk, we are going to see examples for all these 3 scenarios. Now that I have introduced the setup, what are the challenges in designing such a lifelong learning system? Okay, so the first challenge that I want to talk about is the problem of non-stationarity and catastrophic forgetting. Now, what is catastrophic forgetting? Like, so now, let's say I have a neural network which is learning the task A. But this ellipse that you're seeing is the set of parameter configurations which are good enough or like the best possible configuration for task A. Okay, now my gradient descent has found this theta star A. Now I have to learn a new task B, and this is the solution set for task B. Okay, now from the figure we can see that there is actually some intersection point, like which is a parameter configuration which is good for both task A and task B, right? Now, if I do naive gradient descent, there is actually a chance that it is going to just focus on task B and find a solution which is good enough for task B at the cost of doing like hurting the performance in task A, right? Like, so this is what we are going to define as catastrophic forgetting. Now, you could also have like a really bad algorithm which tries to balance between both the tasks, but it is good for nothing. But what we are really looking for is an optimal algorithm which will exactly find the right configuration which is useful for both the tasks. Okay, so now this is challenging. So how do we design systems which will learn new tasks without forgetting the previous tasks? And the second challenge that exists in lifelong learning, which is often less explored, is the problem of capacity saturation. Okay, now when I say a machine learning system, like nowadays the default machine learning system is a neural network, right? Like, so a neural network is a finite capacity parametric model. Now, this means that there is a finite maximum capacity that this network could have. Right. So now if I use this system for task incremental learning, like I'll be learning let's say 5 tasks, then 20 tasks, 50 tasks. And like the moment I learn 100 tasks in this hypothetical example, like I run out of capacity. Okay. Now when I run out of capacity, there are like a couple of options for the system, right? Like, so one, if you want to not forget the previous tasks, then you don't learn anything new so that you can preserve the knowledge, right? That is not interesting. The second possibility that could happen is the system is going to unlearn some previous tasks so that it can learn the new task, right? You know, this leads to catastrophic forgetting. So how do we solve this capacity saturation issue, right? This is the second central challenge in lifelong learning. Now, there has been a lot of work that has been done in the literature to solve these problems in the last 5 to 7 years. Like, so for example, there's one line of work where people think about how can we find the most important parameters for a particular task and freeze them or don't change them too much so that when you're learning a new task, you don't forget the previous task, right? Like, so some examples include EWC, like elastic weight consolidation, or gradient episodic memory, and so on. Now there is a second class of solutions, which are called rehearsal-based methods. Now, the idea here is like there are algorithms like ER or ICAL. Like, so the idea here is you store some examples from the previous task and you replay these examples to the system again and again so that the system doesn't forget the previous task. Okay. There is also parameter isolation methods like PACNet, where the idea is you isolate the parameters responsible for the last task and you preserve them, and then you use the rest of the parameters for the rest of the task. Okay. And when it comes to capacity saturation, there is not a lot of work that has been done. There are like some naive solutions like progressive neural networks, like where the idea is to add like one column of the neural network for every task, which is costly. And there are also some smarter ways of doing this, like learning to grow. Okay. If I have to summarize, like the idea of lifelong learning, like it is all about the trade-off between stability and plasticity of your model. Okay. So I want a model which is stable enough that it will not forget the previous tasks. But at the same time, I want this model to be plastic enough so that it can learn new tasks without forgetting the previous task, right? Like, so now this trade-off is the fundamental dilemma in any lifelong learning system. And one way to solve this problem is to see how we can efficiently do forward transfer and backward transfer between the tasks. Okay, now with this bit of introduction, like, so I want to talk about like few algorithmic solutions that we have developed in my lab, and also very quickly some of the applications and benchmarks that we have designed, which might be of interest to you, like if you are interested in lifelong learning. Okay, so first,
Sarah, just before starting your algorithm, could you please clarify that the difference between lifelong learning and the different like multitask learning, in the sense that each task has its own model. So what you're interested is not really defining a new model or exchanging between different models. You want to have a single model that does all of them, right?
Yes.
Okay, I see. Thank you.
Okay, so first I want to talk about this new work, task-based accumulated gradients for lifelong learning. But I should have updated the slide, like, so the preprint is already available in archive. So I think it just got out a couple of days back. So this is like a really fresh work, by my student Pranshu, and this is also something that I'm really excited about. So this this project aims to design new optimization methods for lifelong learning systems. Okay. Now, before we do that, like, we need to justify why we need a new optimization method. Like, so why don't we just use the standard optimization methods that people use in the literature, right? Like, so I want to give the justification with this one slide introduction to RMS prop. So in the left side, you see the SGD update equation, which I don't need to explain. But in the right side, you see the RMS prop update equation. Okay, so now this is an example of adaptive optimization algorithm, like RMS prop or ADAM or ADAGRAD. So these algorithms adapt their learning rate so that they have accelerated convergence. And in general, like when you are in a single task scenario, like you often use, I think, ADAM as the default optimizer because it converges much faster than SGD, right? Now, in the lifelong learning literature, nobody uses ADAM. Like, so almost every paper uses only SGD. So it's simply because of the observation that any of these adaptive optimizers forget more severely than SGD. Okay, now why is that the case? So now let's look at how RMS prop works, right? Like, so you are dividing the learning rate eta by the root mean square of the gradients, right? Like, so you have this Vn, which is a running average of Gn squares, and you are taking a square root of that, right? Like, so now what is the intuition behind this? Like, so if you see really large gradients, the denominator is going to be large, so the learning rate is reduced accordingly. On the other hand, this algorithm becomes more useful when you see very small gradients. So when you see very small gradients, the denominator is small, which means the learning rate is going to be aggressively increased, right? Like, so in some sense, these adaptive gradient methods are aggressive in optimizing. Okay. Now, there is a problem in doing this in lifelong learning setting, because when you're trying to aggressively optimize for task B, there's a very high chance that you will not care about task A. You will shift quickly to the non-intersection region, right? So that is why SGD forgets less when compared to RMS prop and ADAM. Okay. Now, this project was an attempt to fix this issue of adaptive gradient methods. And before we do that, like, we need to set up some requirements, right? Like, so like the idea here is to really design this adaptive learning rate based on the task information. Okay. So now, for example, if the tasks are uncorrelated, then it could lead to catastrophic forgetting. So I have to be very careful in my learning step. So I want smaller learning rate if the tasks are uncorrelated. Okay. On the other hand, if the tasks are correlated, then it means that I will not forget things. So I can actually aggressively optimize. Now, this is when I can have higher learning rate and do knowledge transfer, right? Like, so now this is exactly what our optimization method is doing. So we are not proposing a new optimizer, like rather than that, like we are proposing a wrapper to all the existing adaptive optimizer methods. Okay, so I'm going to explain the wrapper with RMS prop. So we call it tag RMS prop, but you could really do tag Adam or tag Adagrad, whatever you want. Okay, now this is the update equation for tag RMS prop. Now it looks almost like the RMS prop update equation, except for this term, right? So now this term WNVN is going to be just VN1 for the first task. So in the first task, it acts exactly like RMS prop. But when the second task starts, I'm going to maintain separate gradient statistics for the second task, the GN square value. Now I'm going to combine these two gradient statistics from task A and task B by using this alpha. Okay. Now what is this alpha doing? Like, so I don't want to explain the technical part of this equation, but I'll give you the intuition. So M1 captures the first order moments of the task. Like, so it's just a running average of GN. Now I do a dot product between two tasks gradients. If the dot product is higher, it means the tasks are similar, which means the learning rate should be smaller, right? So that is achieved by this alpha n equation, but maybe I will not spend time in explaining how that is achieved in the equation. So this is tag RMS prop. It, in some sense, automatically decides the learning rate based on how similar the tasks are. Now, I'll show you some results. First, let's start with this basic experiment where we basically do lifelong learning over a series of tasks. This is an example of a task incremental scenario. Like, so we have tasks like C400, mini ImageNet, CUB, or 5 dataset problem, where every task has like every dataset here. Like, for example, in C400, we have 20 different tasks where each task is a 5-class problem. Okay, so you have a bunch of tasks, and you see the basic optimizers like that we normally use versus the tag versions of them. Okay, now we don't use any solution for lifelong learning here except for the tag version of the optimizers. Okay, so now in the left side you see accuracy, which should be higher. In the right side you see forgetting, which should be lower. But for the purpose of this talk, let's just focus on the left side. So specifically, I want you to look at the split CUB here. So you can see that SGD is actually much better than ADAM, which is a common observation in the literature. Okay, now the tag Adam actually gets a boost in performance, and in fact it beats SGD, and hence it's better than SGD, right? Like, so now, as far as we know, this is the first time an adaptive optimizer can be trusted and used in a lifelong learning scenario, or in other words, like we have kind of fixed the problem with these adaptive optimizer methods. So here are like, okay, maybe then the next obvious question is, how is this happening? Like, what is the intuition behind this, right? Like, so these graphs actually verify our intuitions from those two requirement slides. Okay, so you can see that in this particular example, the alpha value decreases. So when the alpha value decreases, the gap between the original RMS prop and the tag RMS prop is increased. So there is a boost in performance for tag RMS prop because it exploited the fact that this particular task 9 is similar to the previous task. So I should aggressively optimize. Okay. Now, similarly, you can see the thing happening in other tasks as well. So here is a comparison of tag with a bunch of state-of-the-art lifelong learning algorithms like EWC, AGEM, ER, and so on. And you can see that like the one-line summary is really tag RMS prop is doing better than any of the lifelong learning solutions that has been proposed so far. Now, what is interesting about tag RMS prop is it is just an optimization algorithm, right? Like it is not an algorithm for, it's not a training algorithm for lifelong learning. It is just an optimization algorithm, which means it's complementary to all these state-of-the-art lifelong learning algorithms. So I should be able to combine tag RMS prop with these state-of-the-art algorithms and get even better state-of-the-art performance. So that is exactly what is happening here. Like, so you can see, for example, in the 5 data set, this blue line is experience replay, like the previous state-of-the-art algorithm for lifelong learning. And you can see that experience replay is using SGD. So you switch it to RMS prop when the performance drops. Okay. On the other hand, if you switch from SGD to tag RMS prop, like you get like 10% improvement in accuracy. And this is a new state of the art for this algorithm, like for this task. So as a summary, lifelong learning really requires rethinking optimizers. Like, so we are kind of the optimization community has overfitted to single task scenarios. Like, so if you want to move from single task to multitask settings, probably we need to rethink how we design our optimization algorithms. And we also propose tag, a general purpose wrapper, a general wrapper on top of existing optimizers. And this is probably the first work to show that you can successively use adaptive optimizers for lifelong learning. So we have a method tag Adam, which is better than SGD, which used to be better than Adam, right? Okay. So maybe I can take, well, I think Wahid said questions in the end, but I can take a question now if there is any question about tag.
It's totally up to you. So
okay,
please.
Yeah. So I can take, I can take questions here before moving to the next part.
Hey, maybe I can have a question. So does that assume that all the tasks are parameterized in the same way? Because you need to make sure that otherwise the gradient is not going to match.
So sorry, can you repeat the question?
So basically, do you assume all the tasks are parameterized in the same way? So for example, you cannot have one task being classification, the other task being, let's say, semantic segmentation.
No, you can do that. Like, so like as long as you have like a common body for the neural network with just multiple heads, that is what we do in task incremental learning. Like, so all the examples that I showed, like you have the common neural network, and then there are multiple heads for the tasks. So now the heads are never changed, right? When you're learning a new task, it's only the common part which is changed, which is where we use tag Adam.
Oh, you only update the backbone. Okay, I see. Thanks.
Yes. Okay, any other questions?
Well, I have a question myself. I keep one for the end, but yeah, I prefer if you think that we have time, I ask the question.
Yeah.
Okay, so when you talk about lifelong learning and also learning through time, because like of data coming, data streaming, you also consider that people who have this access to the device, like you mentioned, like iPhone, they want to run it on the edge, right? For many reasons, like privacy reasons. So we have this federated learning as a sort of a tool to do this, like sort of edge device learning. Would you think that this algorithm needs to be modified if it goes to the edge devices?
Okay, that's a good question. So, like for example, like if you look at the previous state of the art that I mentioned, right? It's an experience replay. So experience replay is not a very good algorithm for like for example, like if you care about the privacy with the data, like if you cannot store examples, you cannot do experience replay. Similarly, if you are in the edge, like we're learning on edge devices, like then you don't have a lot of memory, so you cannot use experience replay, right? Like so now, if privacy is your problem, you could use tag RM as prop or tag Adam, but for learning on edge, it's still not possible because it requires a lot of memory. Like so, like because we need to keep some gradient statistics from the previous tasks, which is actually costly.
Mm-hmm.
But like one of our active research currently is to see how can we reduce the memory print of tag Adam so that we achieve the same performance, but with probably lesser memory.
Thank you.
Okay, so then maybe we can continue with the next question that I want to ask, which is like now I want to ask like a very relevant question for the current progress in machine learning. Like, so we have been designing larger and larger models. Like Google and OpenAI are competing with each other on designing billion parameter and trillion parameter networks. Now, when you have trillion parameters in your neural network, is forgetting really a concern, right? Like, so like, is it true that these models would just remember everything and never forget, right? Like, so like we wanted to ask, answer this question through a large scale study of forgetting in larger models. So this is like a work by Sanket from CMU, who was visiting us last summer, and also my PhD student Darshan. It's currently under preparation for Unix, like so it should be out in archive in a couple of weeks. It's a very large project, but I'm just going to give you a very small snapshot, snapshot of interesting results. Okay, so for this project, like so we are considering language domain. Like so, like we took 15 different NLP classification tasks, like with different characteristics. Like some are single tasks, like some are binary labels, some are multi labels. Like there's class imbalance. There is like different number of examples in every task and so on. Okay, so this is a very challenging like set of classification tasks, and we wanted to study how these large-scale models would learn these tasks in a lifelong learning setting. Okay, so for the purpose of these experiments, like we're going to use BERT, which is a large pre-trained model. And like in the right side, you see the multitask learning performance, which is approximately 75%. In the left side, you see the naive fine-tuning performance, where you just learn one task after another without any adaptations for lifelong learning scenarios. Okay, so you see that there is forgetting that is happening, like so 53 to 75%. And just to give you a bit more details, like, so here there are 15 tasks. We consider 5 different task ordering so that the results are not based on one specific task ordering. And like when I say BERT WX/RY, it means I'm storing X examples per label and replay them for Y percentage time, like in replay-based methods. Okay, so in the middle, you see 2 state-of-the-art solutions from the literature, like EWC, which is like a replay-free method, and an experience replay, which is using the idea of samples, storing samples in the memory. Okay, now you can see that experience replay achieves 68% when I store 50 examples per class and replay them 100% of the time. So it seems to be very stronger when compared to EWC, which is very intuitive. Now the next question is how important is memory, right? So in this table, like you see that when you store 50 examples per class, you get 68%. And when you store just 10 examples per class, you don't lose a lot of performance, like you just lose a little bit. Okay. Of course, when you go to the other extreme, like 1 example per class, like the performance is very close to 0 examples. Now this is about the memory. Now the next question is, how important is it to rehearse the previous knowledge? Like how frequent should I do the rehearsal, right? Like so we have some interesting results here. Like so we show that with just 10% rehearsal, you can get almost same performance as 100% rehearsal. So now this is interesting because I can save 90% of my computation and still get the same performance, right? Like so in some sense, these large models don't forget heavily. Like so, like with just a little bit of replay, they are able to recall like the task again. Now there is also another like deep question here, which is like, if I pre-train these large models, is it going to help me with catastrophic forgetting, right? So now to study this, like, so we use digital BERT, which is a miniature version of BERT. Like, so as an academic lab, like we don't have enough compute to run big large language model experiments. Like, so we went for digital BERT, where like we compare the pre-trained version of digital BERT in lifelong learning versus random initialization. So you can see that the random initialization model achieves 45%, and the digital BERT with pre-training achieves 62%, like, which means to some extent, pre-training actually alleviates catastrophic forgetting. So to summarize, like this project actually asks more questions than like the number of questions it answers. So that is what is interesting about this research. So like there are a few questions that we need to think more, like for example, do models really forget, right? Like, so if the models are able to get their performance back with just 10% of replay, or sometimes even 5% of replay, then did they really forget, right? Like, so maybe the way in which we evaluate forgetting is flawed, right? Like, so for example, when you evaluate a human, like you just tell them, I'm going to test you on this topic tomorrow. Like the student goes and like revises the concepts and come back for the exam, right? Like, so we don't give that revision time for systems. Like, so maybe we need to give them some time to do some few shot learning so that they can retrieve back their memory about the previous tasks. Now, the pre-trained models, it seems to be the case that they are helping in reducing the forgetting. And there is also another interesting question that we try to answer in this paper, which is not part of this presentation, is like, when is interference catastrophic, right? Like, so there has been a lot of work in the literature which says that if you have unrelated tasks, then that leads to forgetting, okay? But we have some contradicting evidence in the paper which shows that it's actually the related tasks which are more dangerous than unrelated tasks, simply because they can easily clash in the representation space if you don't deal with them. Okay, so now, like, finally, I just want to talk about like another flavor of algorithm. Like, so we focused too much on forgetting, So I want to focus a bit on the capacity saturation problem. So for this part, I am going to talk about a part of this big research project, towards training RNNs for lifelong learning. This is the work done by Shangun, who was at Mila before. Now he's at Facebook Research. Now this is the goal of this project was different, but I'm taking the piece which is useful for capacity saturation part. Okay, so let's recap. What would be an ideal lifelong learning system? So it should have knowledge retention capability, no forgetting. It should have knowledge transfer capability. It should be parameter efficient, and also it should have some model expansion capacity whenever it runs out of capacity. Right now, for the purpose of this study, we took gradient episodic memory, which was the then state of the art when we started the project in 2018. So I'll give you a very quick introduction to gradient episodic memory. This is an algorithm to solve catastrophic forgetting or alleviate catastrophic forgetting. Now, the basic idea is you store some examples from the previous task. Now, when you're training on the current task, you compute gradients with respect to the current task, and you also compute gradients with respect to the previous tasks. You make sure that these two gradients don't clash each other. Okay, so you can pose this as a constrained optimization problem, and you can solve this constrained optimization problem for every update step. And you do gradient projections to solve, to avoid these clashes. Okay, so now that is what GEM is doing. Okay, now if you look at what characteristics that GEM satisfies, it has knowledge retention, it is trying not to forget. It has knowledge transfer. It is parameter efficient, but it does not have any model expansion capabilities. Okay, now this is problematic because the moment you try to add these regularizers to updates, then you are eating up some capacity, right? So now these models are going to stop learning at some point. Okay, so we will see that empirically. So well, I'll show that empirically when we come to the experiments. But what we did in this work is really to add this fourth component to GEM. Okay, to do that, we are going to take inspiration from this idea called net-to-net. So net-to-net is a capacity expansion procedure proposed by Chen and Goodfellow in 2015. I'm going to explain it with this very simple cartoonish neural network with 3 units. I want to extend this neural network to a 5-unit neural network. Okay, now how do I do that? The procedure is really simple. So you take the first 3 weights, you copy them. For the remaining 2 units, you randomly sample 1 out of these 3 weights. Okay, now given that I have used W3 and W1 twice, I'm going to divide the corresponding outputs by 2. Now this makes sure that these 2 neural networks implement the same mapping function from X to Y, right? So whatever I multiplied is taken care of by division. Now, we cannot train this as such. We need to add a little bit of noise to break the symmetry, or the condition number of these matrices are going to be extremely bad. In fact, it's infinite because of the low rank nature here, right? So we want to add small random noise to break the symmetry. Now, this is the idea. So now we can apply this to any neural network that we have. So let's see how it works in practice. So in this case, I have a copy task, which is basically copying a sequence of vectors from input to output. And you see the performance of large LSTM, which is a big LSTM model, and a small LSTM, which has half the capacity of the large LSTM. Okay. Now you see it is the large LSTM. It learns. This is the current task performance, and it actually stops learning at 13th task. Okay. On the other hand, if I add GEM capability to this large LSTM, you can see that there is a constraint. So the performance in current task is not as good as it used to be. Also, it stops learning at the 10th task itself because it ran out of capacity. Okay. Now, our method is the blue line, where you have a smaller LSTM, which learns. It also stops earlier at 7th task. Now, when it stops at the 7th task, we use the net-to-net expansion procedure. So now it continues learning, and it actually learns more than the large LSTM with GEM. Okay. Now, if you look at the backward transfer, large LSTM GEM is my upper bound, and you can see that the small LSTM GEM with net-to-net actually achieves performance which is very close to the upper bound than the existing algorithms. Okay, so but I think I spent all my time on algorithms. So I'm going to very quickly go over some of the applications and benchmarks that we have designed. So the first one is a computer vision benchmark. which is called Incremental Implicitly Refined Classification. This is a work by my students Mohammed and Mushtaba, which will be presented at CVPR this year. So this is based on our inspirations from how humans learn concepts. Okay, so like let's say like we see the scenario, like we teach a kid what are these objects, right? Like so like you probably say, oh, these are birds and bears, right? Like so now as the kid grows, like you are going to, it's going to, like he or she is going to refine the concepts as they develop more knowledge, right? Like so you will start recognizing that, oh, this is a hen, this is a cock, and then you will also start recognizing that this is a polar bear and brown bear and so on, right? Like so as humans, we refine our concepts as we mature, right? Like so now the question that started this project is like, do our computer vision systems have this class refinement capability, right? Like so well, the obvious answer is no. And like how do we come up with systems which has this capability? So we propose a task to do that. So in this task, we start with a bunch of base classes, and then we introduce a bunch of new classes once in a while. And these new classes could be like a very specific instantiation of the old class. Okay, so for example, like we introduce bears, and then we introduce a polar bear, which is like a type of polar bear, right? Like so when we introduce polar bear, like we don't say that this is both bear and polar bear. We just say this is a polar bear. And we expect the model to implicitly learn the hierarchy of classes and hence acquire this world knowledge just through this like partial training. Okay, now this like we propose like the benchmark in both CIFAR and Imagenet. And in the case of Imagenet, like we have two versions, like one with 10 tasks and one with 35 tasks, so that you can use the smaller version for compute reasons or for prototyping. So I just want to quickly show some results. Like so, like for example, in this case, in the case of CIFAR benchmark, so the pink line is the upper bound, like it's the incremental joint training with all the classes, and the gold line is the upper bound for lifelong learning. Okay, so this is like an experience replay method with infinite buffer, so it can store all the examples. And the rest of the colors are other lifelong learning methods. And you can see that this gap between gold and other methods is the effect of catastrophic forgetting, but this gap is the effect of incomplete information, like during knowledge acquisition. Okay, so in some sense, while most of the existing benchmark focus just on catastrophic forgetting, like we attempted to focus on other interesting problems in lifelong learning, which includes things like incomplete information. Now here is the performance in Imagenet. Of course, we cannot run upper bounds for Imagenet. It's going to take a couple of years to run these experiments. But you can see like the message here is the current state of lifelong learning algorithms is really, really bad. Like, so there is a huge gap that needs to be filled. So there's more room for research here. And I also want to very quickly talk about another application, but this time in reinforcement learning. So this is the work by my students Hari and Akhilesh, like so, which just got accepted at ICML last week. So this is the idea of using continuous coordination as a realistic scenario for lifelong learning. Okay, now this work deals with multi-agent reinforcement learning. So specifically, we use this game called Hanabi, which is a benchmark for AA that we proposed a couple of years back in this AAJ journal. So this is like a 2 to 5 player, partially observable cooperative game. So where you have to cooperate with other players to win the game. Okay. Now in the original paper, we proposed a state-of-the-art algorithm, like which was based on the idea of self-play, an agent playing along with itself so that it can learn to improve, right? Like now there is a problem here, right? So like we were able to achieve a self-play agent with a score of 24 out of 25, which is very good. But then when we put these agents to play with other agents, they completely break. Their score was like 0 to 5. Okay. Now this is really bad considering our final goal, which is to have reinforcement learning agents with humans in the loop, right? Like so, like for example, imagine self-driving cars in the road. Like so, there might be a car from Google, there might be a car from Waymo, there might be a car from Apple and so on, right? Like so, now they all have to. They are cars from competing companies, but still they have to cooperate in the road, right? Like, so you have to learn to, they also have to cooperate with the humans in the road. So they have to, like, basically the agents have to learn to cooperate with others in a 0-shot or few-shot fashion. Like, so, and that is not possible with self-play. So this paper proposes that we should move towards decentralized learning algorithms. And one way to do that is really by using the idea of lifelong learning. So So our solution is simple. Like, so you take a bunch of agents which are pre-trained, which all get 24 out of 25, and then you put them through this lifelong learning training. Okay, so where you ask them to learn to play against one agent after another. Finally, they're going to test these agents to perform with completely unseen agents. Okay, so now let's see how these systems work like. So for example, here you see 6 different agents. Their self-play is the diagonal numbers, like they are all 24. Now their cross plays are really bad, right? So now here are some more agents from the literature, which has similar properties. So the orange box that you see is an algorithm called other play, which was the previous state of the art for this problem. Which was using the symmetries in the game to design agents which could learn to coordinate. Okay, now this requires domain knowledge. On the other hand, we propose an algorithm which has no domain knowledge, and that is the right column. Like you can see that this algorithm has learned to play well with all these unseen agents. Okay, so now how do we do that? Like, it is just by applying the existing lifelong learning algorithms. Now, I think if you're interested in computer vision or reinforcement learning for lifelong learning, these are really interesting benchmarks. The papers are in archive. The code to reproduce these benchmarks and the baseline agents are also available in GitHub. So you can make use of these benchmarks in your research. So finally, I would like to end with some of the open questions that I hope to inspire you to consider working on. So for example, lifelong learning requires rethinking optimization, right? As I explained in the TAG project, so there is a lot of interesting research that we can do by considering priors, okay, this is a multitask problem. So how do we deal with this, right? And also there is too much emphasis on knowledge retention and forgetting in the literature. I think we should also start thinking about knowledge acquisition and knowledge reuse, which are the key components to design an artificial general intelligence system, right? And finally, we need more research in dynamic capacity architectures, which can expand their capacity, and I should be able to easily add new input units and new output units to the neural networks, and not have the necessity to retrain them again, right? So these are practically relevant problems, but the questions are very fundamental. So yeah, I think with that, I would stop here and take questions. And if you're interested in any of these problems, I'm also happy to chat offline more.